Hello everyone, welcome to our deep dive into Program 7. Today, we're going to demystify the core of AI reasoning, forward and backward chaining. We'll be using our Python Animal Classification Lab as our playground. By the end of this session, you'll see exactly how logic engines think and how you can implement these strategies in your own code to solve complex problems. Let's get started. Think of an AI logic engine like a mystery machine. It takes in raw data, what we call our knowledge base, and processes it through an inference engine. This base is made of two things: facts, like this animal has fur, and rules, like if it has fur, then it's a mammal. Our goal today is to see how the engine connects these dots to solve the mystery of which animal is which. I love this quote because it sums up our topic perfectly. Intelligence isn't just about memorizing facts, it's about the path you take to discover something new. In logic, there are two main paths we can walk down, one that starts with the clues and moves forward, and another that starts with a suspect and works backward. Both lead to the truth, but the journey is very different. Let's break down the two directions. Imagine you're a hiker on a trail. You follow markers as you find them to see where the path ends. That's forward chaining, data-driven. Now, imagine a detective at a crime scene. They start with the suspect, the goal, and look specifically for clues that link them to the scene. That's backward chaining, goal-driven. One is a search for discovery, the other is a search for proof. Meet our data explorer. Forward chaining starts at the bottom with the raw facts and builds up to a conclusion. In our Python lab, we implement this as a loop that keeps firing rules as long as new facts can be found. It's exhaustive. If there's a conclusion to be drawn, this explorer will find it. It's perfect for when you have a lot of data and you're not quite sure what it tells you yet. Here is our actual knowledge base for today's program. We have these ground truths. A tiger and a cat both have fur, a penguin has feathers and lays eggs, and a sparrow also lays eggs. These are the starting pieces of evidence our data explorer will put into their notebook before looking at the rulebook. Now, let's look at the rulebook. We have two simple but powerful logic rules for our classification. Rule 1 says, if it has fur, it's a mammal. Simple enough. Rule 2 is a bit more complex. It needs both feathers and eggs to be classified as a bird. These if-then statements are the gears that will turn our facts into classifications. Let's trace a tiger. Our system sees the fact tiger has fur. It immediately checks rule 1. Since the if part, fur, is true, it triggers the then part. Just like that, our knowledge base grows by one new fact. The tiger is a mammal. We didn't know that at the start, but our forward chaining explorer found it. Now, look at the penguin. The engine sees two facts, feathers and eggs. It checks rule 2. Since both conditions are met, it successfully concludes that the penguin is a bird. If the penguin only had feathers but didn't lay eggs, this rule wouldn't fire. This shows how forward chaining systematically matches data to rule requirements. Now, let's switch gears and meet the goal detective. Backward chaining is top-down. Instead of looking at every fact, we start with a goal. Is this animal a bird? The detective then goes and looks only for the evidence needed to prove it. It's efficient because it ignores irrelevant data. In Python, we often use recursion to implement this, literally asking the code to go find the proof for this, over and over. Let's watch the detective verify a cat. Step 1. Set the goal. Is the cat a mammal? Step 2. Look for a rule that leads to mammal. We find rule 1, which says we need fur. Step 3. Check the facts for fur, cat. Since it's there, the goal is verified. Notice we never even looked at the eggs or feathers data, because they weren't needed for this specific goal. Verifying the sparrow is a bit more work. Our goal is bird sparrow. Rule 2 tells our detective they need two pieces of evidence: feathers and eggs. They find eggs in the knowledge base, but then they have to keep looking to see if feathers is also true. If any part of the evidence is missing, the detective can't prove the case. This is how backward chaining ensures every requirement is met before reaching a conclusion. So, which one should you choose for your projects? It depends on your strategy. Choose forward chaining if you want to discover everything you can from a mountain of data. It's great for exploration. Choose backward chaining if you have a specific hypothesis to test or a problem to diagnose. It's built for efficiency and verification. It's the difference between a spotlight and a laser beam. In your Python lab, you'll see forward chaining implemented as an iterative loop. It scans the facts, applies matching rules, and repeats until the knowledge base stops growing. This repeat until no changes pattern is the hallmark of data-driven reasoning in code. It's thorough and leaves no stone unturned. Backward chaining in Python looks a bit different. It uses recursion. The function calls itself to go deeper into the proof. If it needs to prove an if part of a rule, it starts a new search for that specific fact. This elegant approach mimics a human detective following a trail of clues until they reach the final answer. Here are the results you should see in your lab. Both forward and backward paths should lead us to the same truth. Our tiger and cat are mammals, and our penguin and sparrow are birds. The logic works. No matter which path you took, the destination remains the same, because our rules and facts were solid. This isn't just for classifying animals. Doctors use backward chaining every day to test hypotheses for symptoms. Game developers use forward chaining so NPCs can decide how to react to a changing game world. Even mathematical software uses these tools to prove complex theorems. These aren't just lab exercises, they are the engines behind modern technology. To wrap up, forward is facts to conclusions, backward is goals back to evidence. Both are essential. As you go on to build more complex AI systems, remember these two paths. Thank you for your time today. Now go out there and build some smart machines. Any questions?